Hi, welcome to the fun probability problem solving sections. And let's take a look at what type of the fun probability problem we are solving today. So let's assume the C1 and the C2 all the way to the Cm is a partition of the sample space S. And let's assume the A and the B are two events in this sample space here. So also we have two conditions. Suppose we know the first ones here is for the events A and B, they are conditional independent. And for all the CIs here, so C1, C2, all the way to Cm. And the second condition is B is independent of all the CIs for all the like C1, C2, all the way to Cm. So right now we need to prove is the A and B, they are independence here. Okay, so let's go ahead, go to our whiteboard and let's start to take a look at how do we solve this type of the problems here. Okay, so before we do that, let's try to list a few very basic things. So for the conditional, so let's try to put here let me use a different color. This is the basic formula we all know. So if I have A given B, right? So this is a conditional probability. It's a probability of the B and the probability of the A intersect B. Okay, so let's use the conditional probability definitions here. So the next, so this is the definition about what is we call this a conditional, right? So let's so this is we call this a conditional probability definition. Okay, then we also say if two events, if A and B, if A and B are independent, then here we said, and then we know the probability A intersect B will be equal to probability of the A times the probability of the B. Or you can say that for the probability A given B, because they are independent, so whether you have this given condition or not, it doesn't matter, it will be PA, right? So the same thing is the probability of the B given A, then these ones here will be PB because, when like A given B, whether B occurred or not will not affect, the probability A happens. So that's why we call this independence here. So let's see here. Those are the few basic definitions we need to know here. So the last ones here. So if we said if A and B are conditional, okay, independent. Okay, so what's if they are conditional independent, then what is the formulas here? So we know if A and B, they are conditional independent. So like here A intersect B, given that for the condition C. All right, so it's very similar like these equations, right? But they do have a condition, it's C's here. So if they are conditional independent, that means the probability of the A given C times the probability the B given C. So the probability A intersect B given C will be equal to the probability of the A given C times the probability the B given C. All right, so those are the three sets of the formula we need to use here. Okay, so now let's try to prove. So the problems here, they want to prove A and B are independent. Okay, so my goals here, if I want to prove A and B are independent, so I want to prove is A intersect B is equal to PA times PB, right? So this is the goal of my proof here, right? So whatever I put it in here, I want to reach this goal. So the A intersect B is equal to the probability A times probability B. And so now let's take a look here. So let's start with the left-hand side, PA intersect B. So the PA intersect B, because right now we know the C1, C2, Cn, they are the partitions, right? So I can rewrite this one is I from 1 to n probability A intersect B intersect Ci, right? So why from here to here, why is based on the what? The law of total probabilities, right? So it's based on the law of the probability. So it's kind of like if this is your sample space, right? So like you have this is C1, C2, C3, C5, right? So this is C1, C2, C3, C4, C5. They are the partition of this sample space. And then if you have this is the A, and then you have this is the B's here, right? So A intersect B will be this spaces here, right? So it will be separated by this space and intersect with each little partitions here. Okay, so this is from the basic is the partition laws here. Okay, now here, okay, so let's see here, because by using the conditional probability, I can rewrite this from I from 1 to n. And then I can use the first ones here, right? So I would say this is P, the CI times here, P the CI times, okay, the probability of the A intersect B and the given CI, right? From this conditional probability definitions. So this is from the conditional probability definitions, right? Okay, now let's see here. The next step here is I from 1 to n. Then this is the probability, the CI. And then these terms here will be probability of the A given CI times the probability of the B given CIs here, right? So this term changed to this term. Why? This is from the conditional probability so this is from the conditional independent definitions, right? So like we defined in here, so what is a conditional independent? That is from these definitions here. Okay, so now let's continue here. So here, this is the summation I from 1, sorry, here should be n's here. So from the n, so here this is the probability of the CI. So this ones here will be probability of the piece, and this is A intersect CI, right? So this is from this term tends to be this terms, right? Okay, and then this term PB given CI, this will be the PBs here. So this is from this term going to here. Why? is because B and CI, they are what? Are independent. Right, so that's why you given CI or not given CI doesn't matter. Okay, so now let's simplify a little bit. So this PCI and this PCI can cancel out. And then here I'm sum I from 1 to n, right? So this is a sum from 1 to n, but the PB, this term PB has nothing with index I, so I can take the PB out. It's just kind of like in algebra, we said this is a constant, right? So we move the PB out. Then here, this is I from 1 to n, probability of the A intersection CI. Okay, so what is this? So this is the one. So what is this here? So this term is going to change to the PA, right? Why? From here, this is from the law of the total probability. Because, right? Because C1 to the Cn is a partitions, right? It's the partition of the sample space S. That's why, the A, so this is equal to the PAs here. Then da here, right? So we proved it. So in here, the PA intersect B, we prove to the PA times PB. So that's how do we say the A and the B are independent, right? Okay, so it's very interesting, the problem, and basically use the definition of the conditional probability and the definition of the conditional independent. What's that mean? And if you have a partition, what is the law of the total probability is about? Hope you enjoyed this probability problem. It's a fun problem. All right, so that's it. So talk to you on the next problems here.